All right, welcome back, everybody. I didn't lose too many. Looks like we got almost a full house. All right. If you will, for one last time in the chat, if you would please type in your full name. This is the last time I'll take roll. Okay, so if you type it in when you get a minute before you leave, make sure you put that in there, okay? All right. Any questions? I'm assuming everybody had time to go on Canvas, look around, see what's going on. You can see that we have a lot of stuff to do this semester in a relatively short period of time. So again, I overemphasize, if you need help, get it early. I'm available. If just let me know, send me an email. Let me know what time works for you. I can probably do time after this session, Tuesday and Thursday. If it doesn't, we'll figure out sometime that we can meet through Zoom, okay? The other aspect too is, you all have the ability to communicate with each other. Feel free to set up a little study group. It's been shown that 2 or 3 people in a little study group works pretty fine, works good. Anything more tends to be more of a party than anything else. So, 2 or 3 people, small groups, you can do either, do your own Zoom or whatever meet or whatever method you can meet, or do an email back and forth, either way. So get some help, get it early. All right, any questions before I continue? Any questions? We ended up on slide number 19. We'll knock that out today. We'll jump into number 2 and go from there. Okay, those of you who just came in, when you get a chance, type in the chat your full name, please. That is the last time I will take roll. Okay. All right, that's good. We got a full house, 20 people. Actually 19 with me, 20. All right, well, let us continue then. Let me share. We were just finishing up. We just finished up slide number 19, okay, where we were talking about the physical change. Now, the thing to remember about physical versus chemical change is, with respect to change, physical change, we do nothing to convert the chemical structure. If we have, for example, H2O, which is the formula for water, if it's frozen as a solid, that's its physical change. When we heat it up, it goes to liquid. It still remains H2O. We have done nothing to convert or change the chemical structure, okay? And then it goes on to the gas phase, and it still remains at H2O. So those are the physical properties, solid, liquid, gas, for example, and the physical change is going from these different properties, different phases, and still remaining structurally the same. Compared, in contrast to a chemical change, what we do is literally destroy the chemical structure completely and make something else, okay? A good example would be baking soda, good old-fashioned sodium bicarbonate. When you heat that decomposes and breaks down to make some products. One of them is carbon dioxide. That's why you put baking soda in cooking items when you bake things, because as you bake it, it breaks it down, creates carbon dioxide, causes your cookies to rise. Otherwise, no rising of the cookies, okay? So that's a complete chemical change. Okay, so keep those 2 things separate. All right, so more on physical changes. And one thing is this: atoms, which these chemicals are made up of, and they're put together in certain ways, bonded to each other. They're always in a constant movement. Now, if they're in a solid form, obviously they can't move relative to each other. But when we talk about movement, we're talking about 2 types. One, relative to each other, if they're in the gas or the liquid phase. But in the solid, they're kind of frozen in place. And so, hold on one second. I got somebody at the door. Let me stop for a second, okay? Oh, my apologies. Okay. All right. So as I stated, there's atoms are constantly moving, molecules are moving, whether they're moving relative to each other or they're moving within each other. They're still vibrating and going forth with respect to the bonds. Okay. So there's a constant movement. All right. Excuse me. When you heat ice, as we know, you heat the ice, the ice particles, the water particles are picking up what we call kinetic energy. They're picking up energy. Kinetic energy is a type of energy that causes movement. Okay, and so by these water molecules in the solid phase or anything in the solid phase picking up energy causes the molecules to move to eventually they dissipate and go into the liquid phase. And if you have more kinetic energy into the system, they eventually go into the vapor phase. Okay? So that is what this whole thing is about, is a function, is a process of gaining or losing energy, specifically what we call kinetic energy, which causes these molecules to move a little bit faster. Okay? And therefore, they will go from the solid phase into the liquid phase and finally into the gas phase. All right. Now, with respect to chemical changes, as I stated, when there is a chemical change, the chemical composition of your starting material, remember we have, when we write an equation, and I'm going to do that very quickly, is when we say, well, what are we talking about our starting material? Well, we have reactants. Oh. Okay, reactants, whatever the reactant may be. Okay. Now, if we do something to it, either physical or chemical change, we draw an arrow to show there is a change, and then we produce products. We can produce a product or multiple products. Okay. So that is a chemical process, and that's how we write it. We write it with reactions on the left side of the arrow, products on the right side of the arrow. Okay. Right. So as we stated, these chemical changes, there is AKA chemical reaction. So the starting substance is completely destroyed, and we create a new substance is created. For example, burning fuel, gasoline. Gasoline is made up of a multiple of different types of what we call hydrocarbons. Here, I might as well introduce you to this general formula, which you see here, written here, C subscript X, H subscript X. The X are numbers. Okay, this is a general formula for a type of compound that we have that are called hydrocarbons. Think about carbons is the C part, hydro is the H part, the carbon and the hydrogen. These are compounds that are made up of nothing but carbon and hydrogen, and that's it. Okay. In fact, this is Tuesday we briefly talked about different types of reactions, but this is another type of those 6 reactions that we're eventually going to talk about. But this is a combustion reaction, an example of a combustion. Okay, so next time you are, say, on the backyard cooking up some hamburgers on the propane tank, you have propane, which is a hydrocarbon in the presence of oxygen, and only 2 products that are created in the combustion reaction are carbon dioxide and water. Okay, so and you can see here that the hydrocarbon, the CH compound, in the presence of oxygen, completely is transformed structurally to create 2 new products, carbon dioxide and water. Okay. So this is a good example of a chemical change, a chemical reaction. All right. So how do we what are some indicators that possibly, something happened, that there was a reaction, that there is specifically a chemical reaction? Well, there's a number of things that that can happen, but we're just going to talk about some of the simple examples. Okay, one, obviously, anything that burns, that you see burning, or any type of rusting. You get a brand new car or something, and over time you get it to rust. Okay, that is called oxidation of matter. That is a good indication of a chemical change. Okay, two reactants come together. Okay, without giving off a lot of heat, they tend to give bubbles. Bubbles could be a product. Classic example would be Alka-Seltzer. If you look at the ingredients of Alka-Seltzer, you'll find some sodium bicarb, and you probably find some citric acid. Citric acid is, it's an acid. The sodium bicarb is a base. Those two react together to form carbon dioxide. Okay, so that's why that fizzling going on of the Alka-Seltzer tablets. It's just bicarb reacting to form carbon dioxide. But that's a good indication of a reaction proceeding. You're getting gas bubbles with not a lot of heat formed. There are some reactions that when they start off, they're clear. They're liquids, for example, and you put them together, and then a precipitate forms. Okay, that is a good indication. A precipitate is a solid because of the solubility of the new product that is created. It is not as soluble in that solution, so it gets to be cloudy. Milk of magnesia, for example, if you think about it, if you ever take a container of the milk of magnesia, let it sit in the clear container, it will eventually separate. The material, it's a white powder material, will settle to the bottom, and that's a good indication that type of a solid, that you will get two liquids come together and a solid forms a precipitate. You could get things like release of heat. Okay, a release of heat, a good example would be you go to let's say you go to the pharmacy and you buy a heat pack. They buy these heat packs where you get them, smack them together, the two chemicals mixed together, and what happens is the process is what we call exothermic, because it gives off heat and it gets warm. So you got a sore muscle or something, you can put that heat pack on you. Or it can give off light. A lot of the, I'm having a senior moment with those little containers that you break, these plastics you break, and, they form light, okay? Two reactants come together, and one of the products is light. So emission of light is a good indicator of reaction, or they could be a change of color. You put two reactants together and they completely change into a new color of whatever the material is. It could become yellow, blue, whatever. Or it could give an essence and smell, either be a bad one or a one that smells pretty good. For example, a type of compounds called esters, and that's a combination of what we call an organic or carboxylic acid and an alcohol. Separately, they smell not the best, but you put them together and they form this ester, and boy, these things smell pretty good. Things like wintergreen, if you like to eat wintergreen tablets, that's a combination of these two compounds, okay, giving off an odor. And then the converse is that too, they could create an odor that's pretty bad. All right, so let's talk about specifically a specific example of a chemical reaction. Also, you will see here that we're going to learn to do what this paragraph says, is to take the words that you're given and convert the words into a chemical formula. Okay, so if we look at this thing, it says chemical reaction between sodium metal, and they give you the formula for sodium, and chlorine gas, and they give you the formula for chlorine gas. Okay, when they react, they produce a salt, and the formula is NaCl, right? Which is totally different chemical and formula from the reactants. So what they've done is giving you a sentence or two of a chemical reaction. And then what we're going to do right now, we're just beginning, but we will eventually be able to take that couple of sentences and convert it to a chemical reaction. And so as we look at what is written, this is sodium metal. Well, they give you the formula. There's a symbol for sodium. Okay, we're going to learn that these atoms all have formulas and obviously names. Okay, so Na and then subscript in parentheses, I should say S, tells you, designates it as a solid. Okay, and keyword and tells you to use the plus symbol. So sodium metal and, which is plus, chlorine gas, what they give you the formula. Okay, so you write Cl, uppercase C, lowercase l, and then notice there's a subscript 2. Okay, and then in parentheses G, which designates its physical property as a gas. Now the subscript tells you that there are two atoms of chlorine. And if we were to write them like so, this line here between the two chlorines designates a bond, okay? And this is a bond that is being shared between the two chlorine atoms. Now, instead of having to write it CO, a Cl, line Cl, we see there's two chlorine atoms, we put a subscript. So that designates to tell you this is chlorine, 2 chlorines. Now, it has a special name also. When we're going to learn, there are 7 elements that have this property in that they do not exist by themselves. Notice sodium all by itself, no problem. Okay, structurally it's good to go. But the chlorine needs another chlorine atom to be with it to be stable. Here on Earth, it doesn't, it's not very stable by itself. Okay, and so it needs another one to combine with. And we call that diatomic. This is a diatomic element. And there are 7 of them, which we're going to learn which ones they are. This is just one of them. All right, so then let's erase a little bit here. We are taking what we've been given in a paragraph and we're writing it into a chemical reaction. And so the next sentence is they produce, they being the 2 reactants, they produce. So that is the key for an arrow. They produce, that's the key word to say, I got a chemical reaction, here's a chemical arrow. To produce, to form, any of those type of words to utilize it. Something happened. And it produces the salt, sodium chloride. Okay, and this is a very specific type of new compound, which consists of a combination of sodium and, in this case, chlorine. But we have a new name for it now. Okay, might as well introduce you. This element, before anything happens to it, its particular name is chlorine. When the chlorine reacts, it will form chloride. Okay, IDE. We're going to see that a lot. With chloride, fluoride, bromide, so on and so forth. But we'll get a lot more on that in a second. And this is sodium. And so you can see the nomenclature, the name for NaCl is sodium chloride. Okay, so we wrote the formula, the chemical formula given to us in the 2 lines. Now we're going to do one more step that doesn't explain this. Doesn't tell you here. Let me, I erased everything. Sorry about that. Let me rewrite it. And so we have sodium, solid, plus chlorine gas gives us sodium chloride. Okay. All right. Now, one of the laws of physics is the conservation of matter. Okay. If we were here face to face in the lab, I would demonstrate chemical reaction that would demonstrate this property of this law of the conservation of matter. And what I will do is I'll take some sodium bicarb, put it in a balloon, okay? And then get a little container, a flask, put some vinegar, which is acetic acid, okay? Hang that balloon on the side containing that sodium chloride. Take the whole unit, the balloon, let me draw that. I got a little flask here, and then I got a balloon hanging on the side with sodium bicarbonate. Okay, and then here I got a little container with acetic acid, which is also known as vinegar, the general name, okay? And then I would take this whole thing and put it in a balance and weigh it. And it will have an X amount, okay? A weight, whatever the weight would be. Then while it's still in the balance, I would take that balloon and then I would tilt it and force that powder that's in the balloon here to go into the container. A reaction occurs, okay? Balloon fills up and we end up with the flask like this with the balloon filled up with the gas that was formed in that chemical reaction. It's still on the balance. And if we had, 200 grams of material to begin with, after the reaction is done, guess what? We still have 200 grams of material afterwards. There may be a slight difference because that CO is not 100%, but it'd be like 199.9 grams. Totally new compounds have been made, but the total mass of the material formed equals the total mass of the products formed. Okay, and that is an example of conservation of mass. Well, what does that mean for us? That means that when we have any chemical reaction, which we're going to deal with at a later time quite a bit, we have to do what's called balance the chemical reaction. Okay, and bear with me for a second. You can see on the left-hand side, we have 2 chlorides, okay, and 1 sodium on the left-hand side of the reaction. On the right side, we got 1 sodium and we have 1 chloride. Well, it's not balanced because there's 2 chlorides on the left side and 1 on the right side. So what we do is we balance it by putting a coefficient, that is a number in front of the chemical formula. So that means I got 2 sodium chloride molecules. So that results in 2 chlorides. So that 1 here becomes 2, and that 1 for the sodium becomes 2. So now we have upped the sodium. We made the chlorides balance, but we upped the sodium and no big deal. We come to the left, we put a 2 in front of sodium. So now we have a balanced chemical equation. 2 sodiums on the left, 2 on the right. 1 chlorine on the left, 2 on the right. Okay, and so we have made Mother Nature happy and we balance it. Those coefficients in front, it's understood to be a 1 there in front of chlorine. And we don't have to put a 1, but it's understood like in mathematics, there's a 1. There's a ratio, 2 to 1. Recall in the beginning, yesterday, or Tuesday, we talked about this big fancy word called stoichiometry. And I used the examples of a car and 4 tires, a bicycle and 2 tires, etc. Well, the stoichiometry of this reaction is a 2 to 1 ratio. I need 2 sodiums for every 1 chlorine. That is a stoichiometry for this chemical reaction. It's analogous to a bicycle frame and 2 tires. I have a bicycle frame that requires 2 tires. So the ratio between tires and bicycle frame is a 2 to 1. Okay, and that information we're going to utilize down the road when we start doing calculations. So anyway, some other fascinating aspect about this. I told you that one of the big reasons I kind of got into chemistry was, maybe I did, was because I was fascinated by the electrons. The electrons are extremely small. We're going to learn about their relative size, but they're extremely small. But being so small, they have such a big effect on the chemistry. For example, sodium metal for this reaction is extremely hazardous. It's very reactive with water. Excuse me. If you were to take some and put it in water, take a little nugget of it, it will get very reactive. A lot of sparking goes on. Heat is given off. It creates hydrogen gas. A lot of heat. It ignites it. It goes boom. Okay. Very, very hazardous material. It is so hazardous that in order to maintain it, we have to store it in oil. We can't just leave it out to the atmosphere because it's very reactive. So we store it in oil. Chlorine gas, CO2, is a poisonous gas. A lot of municipalities around the US use it to treat water treatment, to get rid of bacteria and so forth, to clarify. So if you happen to live near a municipality, the water treatment plant, and you ever see a yellow puff of smoke, please get up one quick because they had a chlorine gas leak. Very, very poisonous, very hazardous. All right. So we got a very reactive metal, sodium, very poisonous gas. They react together and form something that you can put on your French fries. It's sodium chloride. Of course, not as hazardous as sodium metal or the chlorine gas, but if you got high blood pressure, it could be a problem. But it's not as hazardous, okay? We put it in our food all the time. All right. And the only thing that happened here was this. Two electrons were transferred. We're going to learn more about this down the road here. Two tiny electrons were transferred over. And that exchange of electrons from the sodium and the chlorine, between the sodium and the chlorine, produced this material of sodium chloride, which is not as hazardous as the starting material. Okay. All right. Okay, so glow stick. Thank you, Josh. I couldn't think of the term glow stick. I just read the note. Had a senior moment there. All right, so let's continue here. This is the format. This is the example of pictures of that material. Very, very, like I said, the only thing that got transferred was electrons. Very powerful electrons. It would be analogous to, let's say if, I don't know if you recall Dr. Jekyll, Mr. Hyde character, but if I were to, lose one hair, I'd completely turn, into another being. That's the relative kind of reference point when we talk about loss of electron, because the protons and the electrons are big, hefty things, and the electrons are tiny things, so tiny that we literally give it a zero mass, an absolute, we give it a relative zero mass. But we will know more on that. All right, so here we go. They're asking you to determine whether this is a chemical or a physical change. Okay, now, yes, granted, we have not even discussed how these formulas are or what they are, but that's okay. Okay, here comes your power of observation, your power of analyzing the data and coming to some conclusion. Okay, keeping in mind that when we talked about a physical change, that the chemical structure goes from point A to point B and it doesn't change. It remains the same. It may change with respect to its physical properties, solid, liquid, gas, but chemically, structurally, it remains the same. As compared to a chemical process where the chemical structure, whatever it may be, gets completely converted to something else, okay? Regardless of the physical state the new material is. It just gets converted completely different. All right, so let's take a look at the first one. The first one you see, I got an N, you got an H, and then a subscript 3. Well, to kind of introduce you to things, N is nitrogen, okay? And H is hydrogen, specifically 3 hydrogens, okay? Now, normally in chemistry, in the ones that we're going to be talking about, when we write a formula, 99% of the time, the first atom you see is what we call the central atom. So nitrogen here is the central atom. And then what follows element-wise is bonded around the central atom. So that tells you that you got nitrogen, and then you got 3 hydrogens, and these hydrogens are bonded in some manner, which we're going to learn how they are bonded around the central atom, which is nitrogen. Okay. Then we notice that it is in a gas, physical state. Okay. The arrow tells us something happened. Okay. So we go look at the products, and guess what? We still have NH3. So structurally, it is the same as what we started off as reactants. The only change is the physical state. It went from a gas to a liquid. And so that's an example of what two bits of information you gather. One, I went from a gas to the liquid, which is condensation. So NH3 is a gas condensed back to a liquid, okay? And NH3 in the beginning is still NH3 after the fact. Therefore, what we have here is a physical change, okay? Physical change because nothing happened to it chemically. Now, and NH3, by the way, that is, FYI, is the formula for ammonia. We're gonna use this guy quite a bit. Ammonia, NH3. All right, let's take a look at this, the number 2. Here we go again. We got NH3 in the gas phase, very similar to number 1. Okay, now we got the arrow, but then note the difference is now we have N2, which is chemically totally different from a reactant. And another hint to tell me that something happened was the plus symbol. That's telling me I got 2 different products. I don't know what they are now because I'm new to chemistry here, but I will learn with time. But I can deduce that since I got a plus sign, that tells me I made 2 products, at least, of something, okay? So that tells me if I can see a plus, guess what? I got a chemical change here, okay? Because I completely changed the structure of NH3 or ammonia. Completely change it to make 2 new products, specifically N2, which is nitrogen gas, okay, and H2, which is hydrogen gas. Notice the subscript, okay? Remember the example we did earlier? We had chlorine was 2 chlorines together, 2 nitrogens together with a subscript, 2 hydrogens together. Guess what? Remember, those were the diatomic, di meaning 2 atoms, diatomic, okay? And there are 7 of them. You've now been exposed to 3 of them. Eventually, we're going to get 4, the other 4, okay? Which I think you know what one of them would be because you need it to breathe every day, okay? Oxygen. Oxygen is also diatomic. All right, so now we got a physical change. Notice that it is also balanced, okay? There's a 2 in front of ammonia, okay? And that says I have 2 nitrogens and a total of 6 hydrogens because I have 2 molecules of ammonia. Another way to see that is this. I got, write it longhand, NH3. That's what that 2 is telling me. I got 2 ammonia molecules, okay? And they break down to form 1 nitrogen plus 3 hydrogen molecules, okay? So that is that formula, that reaction written longhand. Notice I got a total of 6 hydrogens on the left-hand side. Each ammonia molecule has 3, so total 6. On the right-hand side, I have 6 hydrogens in the form of hydrogen gas, H2, diatomic. And then I got 2 nitrogens. Okay, so instead of having to write it all like this longhand, we make it shorthand to put the coefficients in front. That 3 is a coefficient. Now, here's something about the coefficient versus the subscript. Once we establish what the subscript is, that is etched in stone. We don't ever change the subscript. The coefficient, that's the big number in front, we can change that all day long, okay? But once the subscript is set, that is set, and we're going to learn how to determine that, and that is the structure of that compound. So we don't change the subscript, but we change the coefficient all day long. All right, number 3. Okay, it looks like water. You got H2O, but there's a subscript 2, meaning that this compound, okay, whatever it may be, has 2 hydrogens. This molecule has 2 hydrogens and 2 oxygens. Okay? All right, now I'll tell you what that is in a bit. We look at the reaction, it's in the liquid form. We go over to the product side, and lo and behold, we got a plus symbol. Automatically tells me I got a chemical change because I'm producing 2 products, specifically hydrogen gas and oxygen. So without question, I don't have to go any further. I can deduce that this is a chemical process, even though I don't know what the chemicals are. I'm going to let you know what they are. Okay. If you ever cut yourself and you put a little liquid on your cut, you use H2O2. If you ever use it to dye some hair, you use H2O2, which is AKA hydrogen peroxide. Okay, that is the formula for hydrogen peroxide. Excuse me. All right, number 4. Same formula, H2O2, AKA hydrogen peroxide. In the liquid phase, we look at the arrow, look at the product, and it remains H2O2. Okay, so nothing happened to it chemically. Therefore, and the only thing we can see is it went from liquid to a solid. Okay, we call that freezing. Right, it went from a liquid to a solid. And so this is an example of a physical process. And then finally, the last one, again, you may not know what it is, but I hope that you pick up on something I just mentioned earlier. Remember I was showing you the general formula C6H6? Remember that? Where X's represent numbers. In fact, the smallest one is C1H4, okay? That is the smallest one, that's called methane. That, and CXHX represents hydrocarbons. Number 5 here, C6H6 represents a hydrocarbon. That's a general name for that hydrocarbon. We may not know what it is specifically, but that's okay. We do recognize that is a hydrocarbon, and hopefully you recognize that in the presence of oxygen, I can burn this stuff, okay, and have a combustion reaction. But we look at the reaction, C6H6 is a liquid. We look at the arrow, formula-wise remain the same, physical state changes, okay? And so what we got here is simply an example of a physical change. Now, I know you don't know what C6H6 is, that's okay, but I'll tell you anyway, that is the formula for what we call benzene. Benzene, which is not a good chemical, it's a carcinogen, causes all kinds of problems. Let me clear this up. All right, so.
I've got a question.
Sure, go ahead.
So if oxygen is diatomic, then how come it's just singular when it's for water?
Because structurally, oxygen by itself in elemental form is diatomic. Okay, so is hydrogen, so is nitrogen. These are elements. We're going to learn when we talk about the elements, all 118 of them. We're going to talk about every one of them, even the major ones, that by and large, all of them except 7 of them exist in nature, at least here on Earth. because they can exist in different forms someplace else, as single entities. But those 7 diatomics, from an energy perspective, are not very stable by themselves. Oxygen atom by himself is not very stable. So what it does, it needs another oxygen element, atom, to combine to form the diatomic. There's 7 of them. Now, once they react, okay, and they are in other forms, there's still oxygen, but the oxygen and water, the oxygen in water, oxygen in the elemental form by itself is a little bit early here, but is two lines which represent 2 bonds between 2 oxygen atoms. But oxygen in another form like water is just a single oxygen by itself. It's bonded to other things, but it's no longer the element oxygen. It is now part of water. Okay? Part of water. Does that make sense to you?
Yeah, so it's not oxygen anymore. It's something
It
else.
is, you got it. It is no longer oxygen anymore. It is something else. Even in this state where you got carbon O2, that is not diatomic, that is carbon dioxide. And so it's no longer oxygen in this form, it is oxygen in the gas carbon dioxide. It's still oxygen. And that's the key thing to remember, that even though, and we're going to learn about this, every element has a specific number, that doesn't change. Okay, oxygen has a specific number in this form, and it remains a specific number in this form. It still has the same number of protons. Okay, it's still oxygen. It just happens to be in a totally different form. Okay. All right. Good question. Yeah. All right. So, which brings us to elements, compounds, and mixtures. All right. So, an element. An element is simply one type of atom itself. Okay, it could be either a single element, like say He, other AKA helium. Okay, we're going to learn that the elements have symbols, which is the first symbol is a capital letter, and it may have a second letter, but that second letter is lowercase, always lowercase, which is important. For example, why is that important? Because if I were to write CO versus C little o, lowercase o, I have 2 different entities, okay? Cobalt is the one I written in the bottom. The top one is carbon monoxide. Totally different species, okay? And so it's very important when we start working with the elements that when we write that second letter, that's going to be lowercase. If we go uppercase both cases, you're no longer talking about the element, you're talking about something completely different, okay? All right, so with respect to elements, I can't break it down any further. Chemically, if I break the element down further, then I start breaking it down into the subatomic particles. All right, so every element has an X number, where we're going to learn about protons, an X number of neutrons, an X number of electrons, okay? And every element, every carbon atom will have the same number, be it in the form of carbon dioxide, be in the form of graphite, carbon, still carbon. Now, with respect to compounds, here's where you got to differentiate too. A compound is a species, a chemical species that is made up of 2 or more different bonded elements, okay? And so we had, for example, the diatomic ones where we have O2, okay, made up of 2 of the same elements. That is an element, even though they're diatomic, it's still an element. But if I go, let's write carbon monoxide. I got carbon and I got oxygen. That is an example of a compound, 2 different elements, okay? 2 different elements, so it is a compound. Now, I can break carbon monoxide down to the elements. And that's how we know we have a compound, because I can break the compound back down to the elements. Okay? Whereas the elements, I can't break them down any further unless I start breaking them into subatomic particles. All right, so then of course, if something is pure, this is pretty self-explanatory. We got just only one type of material. All the particles are the same, all the physical properties, everything about that particles, they're all the same. And it's pure, 100% pure. You know, at least close to it as possible, because nothing really is 100%. As compared to a mixture, where we can have together two more different types of, we can have a compound, or we can have an element, or any combination thereof to make a mixture. Okay? All right, so this flow chart kind of breaks it down for you. If we look at matter, okay, we're starting at matter over here, and then we shoot over to a mixture. You can see the way they're designated. We had these spheres either be diatomic. Notice the red ones are together, two red ones together, which represents a diatomic compound, or element, I should say, not compound, element. It's a molecule. When we generally use the term molecule, we're talking about the diatomic. So a molecule of diatomic element denoted by two round spheres of the same color and the same shape. Okay. So here on the left side, we got a mixture of two elements. Okay. Notice we get the four darker ones and then the two diatomic in red. So we got a mixture of two elements. One of them happens to be diatomic. If we look at the picture on the right-hand side, we got three different colors, which again represents a mixture of some element, you know, three of them specifically, because we got three different colors. Okay. On the far left, when we talk about something that's pure, pretty self-explanatory with respect to the term pure. But when we look at the elements themselves, we have here just one color of round spheres. It could be anything. In this example, they're using neon, but it could be anything, just singular atoms, okay? On the right, we can see that they're diatomic, and hence we call those molecules when they're diatomic elements. Sometimes, occasionally, the molecule term is incorrectly used to explain a lot of other things, but correctly, a molecule generally pertains to a diatomic species. All right, so now if we look at compounds, which consist of two or more different elements, that is what constitutes a compound. So here, we look like, you know, Mickey Mouse ears going on right there, really. So you can see that we have H2O as an example, H2O, where the red represents the oxygen, and the two little smaller yellow color ones represent the hydrogen, okay? And then we got on the right, sodium chloride. An example of that. Okay. All right. Mixtures. Some examples of mixtures, well, metal alloys. Metal alloys are mixtures. Pure metals by themselves are not very functional. Pure gold, pure steel, not steel, pure iron is not very strong. So iron generally is mixed in with some carbon or some other elements and made into stronger material so we can use it to build things. Same as with your gold ring that you may be wearing. Yes, be it 18 karat, 24 karat, it's not 100% gold. Simply because they don't go pure 100% gold is very soft. It doesn't lend itself very well to make jewelry. Brass is a mixture of copper and zinc, okay? And so tap water, for example, sand, granite, these are examples of mixture. Tap water, the tap water we get is a mixture of all kinds of things in your water, metals and so forth. And then the air around us it consists of a variety of different gases. We can have something that's pure, like sodium chloride. We can get sodium chloride, table salt, and really purifying it nice and clean. A diamond, well, to get a pure diamond is kind of tough, but they're out there. Diamond, which is fascinating, is made up of nothing but carbon. Okay, nothing but carbon, and we're going to learn that that carbon consists of 6 protons, but it is the same carbon with respect to the number of protons and so forth that you may make up, say, graphite. Think about this. You got graphite that has some carbon in it. It's very soft and it's a dry lubricant. We use it for multiple things. Very slimy feeling. Okay. And then you got a diamond, which is one of the hardest items on earth, which is also made of carbon. And you might think, well, wait a minute, I got carbon here, same element. Why is there a difference? Well, the difference is because the way the carbon atoms are set relative to each other. Okay, that gives it the strength and the power that diamonds have. And we can do that. You know, we're all familiar with polystyrene. Polystyrene, you make the cups, are very soft, very crushable. They're soluble and a lot of solvents, readily dissolve. But if I play around with the formula, if I play around with polystyrene, I can make it strong enough to actually make wooden lumber out of it. And it's all about how big the polystyrene or the polymer is made. Okay, so distilled water, it can be pure, at least pretty close to it. If you take water and you distill it, that means you heat it up and then condense it into another container, you will make some pure water. Sometimes you're going to do multiple distillations because sometimes organic compounds go with it and they're not 100%. Okay. All right. Couple of questions. A couple of questions. Joshua asked about why graphite is used as lubricant. Simply because it's very slimy. Okay, made of carbon. It's very slimy and it's a lot better than cleaner, I should say, than dealing with oils and stuff. You might be concerned with the material you're working with. You want a dry lubricant rather than a liquid one that can interfere with other aspects of whatever you're working with. And then the difference between true diamonds and the lab diamonds are simply, they're just, both of them are made with a lot of pressure. Okay, we can make diamonds in the lab, but it takes a lot of time and a lot of pressure to make them. So technically speaking, from a chemical perspective, they're made up of the same material. Okay, but from the worth, obviously the diamonds you find naturally are, I believe, a little more expensive. Okay. But both the same. Okay, hope that answers that question. All right. We use a lot of diagrams to depict things. Okay, so this is an example of how to depict, say on the far left, we have that depicts a diatomic element, not compound. Not compound, because first of all, let's look at that. You can see that each sphere is the same color, same everything. So we're looking at the same element. And it's diatomic, but they're bonded together. Okay. When we look at the next one, you can see that we have a central atom here. And then bonded to the central atom, are 2 other elements. So what we have here is a compound. Okay. And then in the far right, we obviously have a mixture of an element, a single atomic element. And there's another one right there. Okay. And then we have a compound, like Mickey Mouse ears, right? They can be represented. We have a dark center, and then we get two elements bonded to the central atom. So we get a mixture on the far of a compound and 2 different elements. At least that's what that is supposed to represent. Mhm. And so here you may see a diagram that says, okay, well, it will classify as an element, a compound, or a mixture. If we look at A is simply a diatomic element. Okay, nothing else in there. If we look at B, we got the dark centerpiece, which represents an atom, and then we got three smaller ones around it. So we have something which is a different color and different size. Obviously, we've got two different elements being represented here. So that would represent a compound. Okay. Remember, a compound by definition is matter that is combined, made up of two, at the minimum, two different elements. C looks like we got a mixture, right? A and B are by themselves, so that if you want to extend the definition, we got a pure element for A, a pure compound for B. Whereas C, we see two different colors. So that represents a mixture. And furthermore, it looks like that's it, two single colors of two different colors, two different sizes. That would say I got a mixture of elements. Okay. D is all one color all by itself, nothing else in there, so it's pure, and it simply represents an element. Okay. E, it looks like we got the dark and the white circles. They're combined together. That represents a compound. There's nothing else in there, so that, again, that would be a pure compound. Whereas F, again, represents a mixture of, looks like two compounds, right? And one diatomic element. We got a mixture going on there. And then G, again, another mixture of a element and a compound. And then finally, you can see here H, just one color. So, and it's very structured, very ordered. I mean, all I can say is an element. Furthermore, I can say, hey, you know what? Probably some kind of a solid. Can a mixture, oh yes, Eduardo, the question is, can a mixture be two or more compounds? Yeah, a mixture can be any combination of anything you can think of, okay? And Josh, you had a question about pencil lead and slimy confusing. Well, pencil lead, there's other things in the pencil lead. Yes, there's some graphite in there. Oh, I got you, yeah. So yeah, there's carbon in there. And we're going to learn that carbon, it's the same carbon that is found, I shouldn't say the same carbon, it's the same element that is found in, let's say, diamonds. And guess what? It's the same element, carbon, the same element found in your body. It has the same number of protons, be it in the form of found in pencil, being in the diamond ring, being part of your muscle structure, same carbon. Okay, so elements. Elements have what we'll do is we'll finish this up here. We'll take a quick break and we'll jump into chapter 2. Okay, so each element has a unique name, a symbol, and a specific number. Okay, now if you had a chance to look at the periodic table, that one should be updated, I believe. If not, there are 118. Okay, there are 118 elements. Okay, now, not too long ago, this one, and these three were found and they were given official names, but our periodic table hasn't been updated. They all being given official names now. But not too long ago, which is, I want to say 2015, these elements were not found. And so we had a lot of blank spaces in. They were predicted, now they're found. So we got 118. Now check this out. You might use this here. powers of deduction here. Okay, notice we start with number 1 right here. We shoot across number 2, then we go 3 over here, and we keep going. And we go back and forth, back and forth, back and forth. This is 119, okay? Excuse me, 118. If, and they are looking for higher ones, 119 will be right here in level number 8, okay? If we can get them made. All right, more on this product table down the road. You notice I have mine kind of marked a little bit different than yours, and that's okay. We'll get to that. I got it marked for a particular reason. All right. So everybody has a unique name, unique symbol, and a number. Okay. 118 of them right now. Now, with respect to the symbol, you either have 1 or 2 letters. If they have 2 letters, the first letter is capitalized, and the second letter is not, lowercase. Okay. For example, HE represents helium. C lowercase a represents calcium. Okay. And C lowercase o represents cobalt. These are all different elements in there. Be careful, as I mentioned, if I use uppercase, then what I'm doing is talking about a totally different species. You know, so uppercase O would be carbon monoxide rather than cobalt. Okay, most symbols are from English names, so H from hydrogen, O from oxygen, He for helium. But there are some that are derive their name from Latin names. So PB comes from the Latin term plumbum, which deals with waterworks. A good way to remember it is plumbing. Okay, lead plumbing. I don't know if you're familiar with this, but sometimes we used to use lead to take lead pipes and connect them. All right. And so plumbing, and then the symbol PB tells me lead. Okay. Sometimes I see a lot of this, LE to be lead. That's not the case. Okay. All right. AU is a symbol for gold, and it comes from Orium, which means golden dawn. Okay. Now, be familiar with, at least at this point in time, with the first 20 elements, okay? And we go back to the periodic table, so we go over that real quick. All right, so we have on the far left, number 1, element number 1, okay? And let me change my color a little bit. Element number 1, starting right here. That is H for hydrogen, okay? Then we go across the periodic table, okay, to He, which is helium. And we shoot back to number 3. Notice in front, on top of each symbol, there's a number. 1, 2 for helium, 3 for Li, which is lithium. Number 4 is beryllium. Number 5 is boron. We hope we jump across the table here. Boron. Number 6, the infamous C for carbon, okay? That 6 is very important. We're going to learn about 6 and 7 and 8, but that 6, you know, when we're talking about carbon and diamonds, carbon and carbon dioxide, carbon and graphite, all those carbon atoms have the number 6 associated. They just happen to be in different forms, okay? Number 7 is N for nitrogen. Number 8 is O for oxygen. Number 9 is F for fluorine. Notice the term fluorine, not to be confused with fluoride. Okay, totally different. This morning when you brush your teeth, if you use they call it fluorinated toothpaste, you brush your teeth with a fluoride, specific type of compound. You didn't brush your teeth with fluorine, okay? Number 10, and E for neon. Number 11, the infamous Na, natrium, sodium. Number G, magnesium. Then we shoot across the table to number 13 for good old Al, Al for aluminum. Si, number 14 is silicon. P, number 15 is phosphorus. Okay. S for number 16 is sulfur. Here is number 17, Cl, lowercase l, for chlorine, not to be confused with the chloride. Okay. We're going to learn some of these elements, depending on which side of this stair step that you see here, their name, when they get converted, changes. And fluorine, when it gets reacted and does other things, gets changed its name to chloride. Chlorine changes to chloride. And if I had to get a guess, what does bromine change its name to? Bromine. Okay. All right. Number 18, Ar for argon. Number 19, good old potassium. And number 20, Ca for calcium. Okay. Calcium. Now, this is the elemental calcium. If you're taking calcium supplements, you are not taking this calcium. You are taking a type of calcium that has lost electrons, okay? Has lost electrons. We're going to have a lot to say about that down the road, not just for, not for calcium, but for these metals, because we're going to learn here that of these 118 elements, 3 classifications. Either they're going to be a metal or a non-metal or a what we call a metalloid, meaning that they have properties of a metal and they have properties of a non-metal. Okay, those are the only 3 classifications: either be a metal, a non-metal, or a metalloid. All right, let's go back. Now, on top of that, those 20, be familiar with these following metals, okay? Ag for silver, Au for gold, Pb for lead, Br for bromine, I for iodine, and Hg for mercury. We will, with time, learn more of it. We're not going to sit here and learn all 118. We will learn some properties about all the elements based on where they're at the periodic table, but we're not going to learn every aspect like all 118. Okay, but I would say a good be familiar at the end, maybe between 40 to 50 of the elements. It's almost about half. Okay. Now, the physical states. When we talk about the physical states, we have to be specific as far as our reference point, okay? We're talking about 25 degrees Celsius and what is called normal atmospheric pressure, okay? So 25 degrees is roughly room temperature. Obviously, the physical state on the surface of the moon will be totally different than, say, in the North Pole, right? Of course, temperature is different. But so at room temperature, ballpark, and in 1 atmosphere. Right now, we sit in about 1 atmosphere pressure, okay? You go up to Colorado, the atmosphere gets a little bit less. You go down deep into the ocean, it gets quite greater, more pressure, but 1 atmosphere. All right. Now, under these conditions, of the 118 elements, only 2 of them are liquids, specifically Hg, which is mercury, and Br subscript 2, which is bromine. It's one of the diatomics. That's why the subscript 2. Okay. Of excuse me, of the 118, we have the physical property of 1, 2, 3, 4, 5. Noble gases. Well, let me show you what the noble gases are. Okay, let's go back to the, okay. The noble gases, 1, 2, 3, is on the far right, right here. Far right. Notice in the far right, they have a Roman numeral 8A. Okay. Notice a lot of them have Roman numeral 3, 4, 5, 6, and 7. Very important bit of information we're going to learn about. Okay. So everybody here, there's 1, 2, 3, 4, 5, 6, and 7 noble gases. They are called noble gases because they are very inert, meaning that they are not very reactive. Okay. Can they react? Yeah, but for Chem 130, these noble gases are inert, they do not react. There's 7 of them. Now those 7 plus 8, 9, 10, 11, 12. So there are 12 elements that are gases. Hydrogen, nitrogen, oxygen, fluorine, chlorine, plus the 7 noble gases gives you a total of 12 elements that are gases at 25 degrees and in 1 atmosphere. There are 2 that are liquids. Okay. And so what does that tell you? That the rest of them are, see, I say 118, right? We got 14 here. Solids. Okay, so at a glance, by picking out the liquid, finding out where they're at, finding out where the 12 gases are, you can determine all the other 104 are solids. So if I were to go to the periodic table and say, hey, boom, element number 64, is it a liquid, gas, or solid? Be able to determine that, okay? Okay, we don't have to memorize the particular property for that particular element. We just have to know which ones are liquids, which ones are gases, the rest of them are all solids at the ambient temperature. Obviously, if we were on the surface of the moon, the sun, everybody would be gases or vapors. All right, so that's the breakdown on that information. Okay, this kind of helps you out with this product table. The ones in yellow are the gases. The 2 pink ones, I think they're pink or purple. I think he says purple up there. They look pink from my screen. The mercury, which I'll highlight for you. Oh, come on. Here's bromine and here's mercury. Those are the 2 liquids. The ones in yellow are gases, and everyone else is a solid. Okay? Everyone else is a solid. All right, I mentioned earlier about the 7 elements that are diatomic here on Earth, okay? And that's their most stable state. This is how they can handle here at 25 degrees in 1 atmosphere. There's 7 of them. And to help you out, you can say, you can use the following: have no fear of ice cold beer or beverage, whatever works for you, okay? Where the H of have is for hydrogen, okay? The N for no is for nitrogen. The F for fear, in fear, is for fluorine. The O for of is oxygen. The I for ice is iodine. C is for chlorine, not carbon, okay, not carbon. And B is for bromine. Those are the of the 117 elements, okay, only 7 are diatomic. And of those 7, only one of them is a liquid at ambient temperature. The rest of them are gases. All right. Now, excuse me. As I mentioned, there's a question. Oh, no, no, no. The question is that periodic table you would need to print out, you write down whatever you need to help you learn whatever you need, okay? If we were on campus, face-to-face, normally I'll pass out a periodic table with no marks, but obviously we're not there, you know, so you have resources in front of you. Just don't, you know, for your homework and your labs, you can use whatever resource you need. Okay, but if the exams are the ones that we have to use the lockdown, that we don't need you going outside on the internet looking for stuff, hopefully. Okay. Yes, PowerPoint slides, Natasha. There, you have a module. If you go into Canvas, check the last module down the bottom, you'll see all the PowerPoint slides. Some of those, I've adjusted them. I don't use them. So if you print them out or use them, just make note, cross out the ones I don't use anymore. Okay, no worries. No. All right, so we have three further classifications, if you will, of the elements. Okay, either it's going to be a metal, okay, a non-metal, or a semi-metal, or another word used is a metalloid, meaning that they have properties. The thing about the semi-metals is they have properties of a metal and properties of a non-metal. Okay, it's very much like a mule. Anybody know where a mule comes from? How to produce a mule?
Is it a donkey and a horse?
You got it. A mule is a combination of a donkey and a horse. And so they have properties of a donkey, and properties of a horse, not quite one or the other. And that's what semi-metals are, okay? Now, on the periodic table on the left hand, there is a stair step, okay? There is a stair step. And that helps you remember who are the metals and who are the non-metals, because on the stair step are the metalloids, okay? Except for aluminum, which is a metal. And now, let me see if I have that shown right here. So you can see here that stair step starting with boron. So we go down this way, then down this way, and across like so. Now, I believe 117 might be a metalloid. I don't have enough information about that. It's one of the new guys. And unfortunately, a lot of these new compounds, elements they make, they don't have a very long shelf life. If you give enough time to figure its properties, they break down very quickly. So for right now, we're just going to leave it there, stop there. So these guys in green are the metalloids, okay? And that follows that stair step of the periodic table. Now, anything to the right of the stair step is this pink area, red area, everybody right there. Plus, don't forget about hydrogen on the far left. Now, hydrogen is placed over there for a reason, and we'll learn why it's over there. But for right now, not to forget about hydrogen, okay? And so those are the non-metals. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 non-metals, okay? And you can see where the metalloids are. And then everybody in blue, including these other elements. Now, here's the thing about the periodic table, which is kind of confusing. Notice this is 58 and there's 57. Normally, this whole group here fits right in there. And then the bottom right here is number 90, fits right after 89, obviously. What that means is and now I have a periodic table to show you what it looks like when it's spread out. It's spread out normally, but what they've done is you pull those two guys down here in the bottom out, they have a specific name, and then shrink in the periodic table to make it a little more easier to read, okay? Plus, thing to note, and don't forget, is notice the Roman numeral sequence on top of each column. Roman numeral 1A, 2A, then it jumps over to 3A, 4A. That Roman numeral is very important. It's going to give us a lot of information to help us out. What they're trying to do is get rid of that nomenclature and use just sequentially 1 through 18. There's pros and cons in using that because the Roman numeral gives us, you'll see here, the Roman numeral gives you a lot of information. Okay, so now you have here the diagram, the metals and the non-metals, okay, and the metalloids. We're not gonna do a lot of work with metalloids, okay? We're gonna be doing a lot of work with non-metals, the nitrogen, oxygen, fluorine, sulfur, chlorine. As far as the noble gases, they're not very reactive, you know. They're not, they're noble gases. So think about it. As far as non-metals are concerned, you know, the ones that are going to be doing the most of the reactions right here, I'm circling them. Right there, yeah. Now, and then of course the hydrogen over here, okay? These guys are non-reactive, okay? So the non-metals can not do a lot of work. Then that means that everybody else are metals. And even at that, most of our work would be dealing with the first two columns and then a few of them inside, okay? We're not going to do a lot of work with the ones sticking out here in the bottom. All right. Now, here's the thing to put in long-term memory, okay, between metals and non-metals. I mentioned earlier that an atom, it consists of protons, neutrons, and electrons, okay? Right now, I'm going to talk about electrons. These electrons have a negative charge. These are the same electrons that, you know, you got bad hair day that's popping up, or, you know, your hair pops up and it's static clean. These are electrons. There are electrons all around us. But there's electrons orbiting around these elements. Now, for metals, they are always going to lose electrons. 100% of the time. For non-metals, gain electrons. That is the nature of the beast about metals and the nature of the beast about non-metals, okay? And the result is the electrons, think of it from a psychological standpoint. If a person loses negativity attitude, do they not become more positive, right? From a human perspective, right? So if you lose electrons, guess what? You become positive in charge because you're losing some negativity, you're losing electrons. On the converse of that, when you gain electrons, you pick up negativity, you become more negative, right? And that's what's going to happen between these metals and the non-metals, okay? Because of the nature of the beast and where they're at on the periodic table, they're going to gain electrons or they're going to lose electrons. And that results in being able to determine who's going to have a negative charge and who's going to have a positive charge. When you drink a juice, when you drink a drink with electrolytes, you are not drinking the elements, okay? You are drinking the elements that either have lost or gained electrons. That is what you are ingesting. The calcium I mentioned earlier, when you take calcium, you get a calcium supplement, it's not the calcium element of calcium. No, you are it's a metal, so you are ingesting positive charged calcium. All right, okay. A lot more in that down the road. So some of the properties of metals, they tend to be shiny in appearance. They're malleable, and that, in other words, you can stretch them out. I worked in the industry of copper plates, and we did a lot of research on copper plates. Eventually the copper plate thickness that I used was two sizes, 1/4 inch thick or 7 millimeter thick. Okay, very thick. But the way they started with a billet of copper, which is about 3 or 4 feet thick, and they rolled it back and forth until they got it down to the thickness that we used. That's that are the properties of metals. Okay, all the metals are solids except mercury. Mercury is a liquid. Mercury used to be used a lot for thermostats, because being a metal, they conduct electricity, and they were able to close the circuit of a thermostat. Not so much mercury is being used anymore. Density, remember that property, that ratio density is mass over volume, that ratio. Okay, the density of metals generally are pretty high, very highly dense. Their melting point, that is a temperature in which they soften up, extremely high to get them melt. That's why when we melt metals, we got these mills out here that melt them down. Well, not as many as we used to, but they require high heat to melt. And because the nature of the beast on metals, they are loaded with electrons on the surface. And because of that, they are good conductors of electricity. They conduct, all our wiring is made up of metals because of their conductivity ability. And being a good conductors of electricity, they're also good conductors of heat. Okay. With respect to nonmetals, in general, they tend to have a dull appearance. Okay. If they're the ones that are solids, they're brittle solids and they're very strong. Many of them are gases. Okay. And their specific density, mass over volume, is relatively low. And they tend to melt at a relatively low temperature as compared to metals that have a very high, maybe a couple thousand degrees, getting it melted. And nonmetals tend to be poor conductors of electricity. Doesn't mean that they don't conduct electricity, but they don't do it as efficiently as well as metals. Okay, and because of that, they're better insulators than they are conductors of heat. So look at the periodic table, be able to determine the name for at least the 20 plus the others that we gave you. Okay, there's slide number 35. Look at your periodic table and be able to determine, any of those elements that you may be given. Is it solid, liquid, or gas? Okay. And as I stated, it's not necessary to memorize the physical property of all 118 elements. You're more than welcome to if you want, but you can determine, okay, here's the 2 liquids, here's the 12 gases. Everybody else has got to be a solid, right? All right. From the stair step, be able to determine, okay, it's a metal, non-metal, or a semi-metal. And then there's only 7 elements that are diatomic. Have no fear of ice cold beverage. Okay, those are the 7 elements that are diatomic. That information is important because remember we went through that exercise where we had written in a couple of sentences a reaction, and we had to convert that reaction into a chemical reaction. And it said sodium reacts in the presence of chlorine. Well, you have to know that chlorine is diatomic. It's not Cl by itself, it's Cl subgroup 2. Okay. All right, and also the physical states, because we're going to learn when we write chemical reactions, we have to write in the physical state. All right. Okay, ladies and gentlemen, chapter 1 is complete. We are done with that. Tell you what, let's take a 15-minute short one, and then we're going to jump into extra calculations, get into some math, not complicated math, but get into math, how to convert factors from point A to point B. We're going to learn a technique because we're going to utilize that technique when we get to the chemical reactions, okay? And it's all about these ratios I talked about. I introduced density, mass over volume, but we can use the same concept in any ratio, dollars per hour, okay? Miles per hour, okay? So anyway, let's come back in 15 minutes. It's about 2:45, and then we'll jump into chapter 2, okay? Let me pause this. Okay, I'm back. Was it? I see a question. Josh had a question about carbon to make things harder. It depends on the material. Iron, carbon is utilized in iron to make steel, plus not only carbon, but there's a number of different other materials that are put into it. But not only the components that can make things a little bit tougher or stronger, but the way they process it is how they process it can make it very stronger. Okay. Yeah, for example, some of the copper I worked with is 99% copper, but it had traces amount of silver and some other components, and that trace amount was enough to give it stronger, give it a lot of strength. Okay, I hope that answers so for carbon question. All right, so that brings us to any other questions before I? Okay. All right, well, we're going to kind of shift gears a little bit, get into some mathematics. And again, I emphasize it's not, high-level mathematics. We're going to be doing some conversion factors. We do, as scientists, we do use the metric system for measurements, but we're going to be using some of the English units to convert from one to the other, okay? And so there are, read chapter 12, obviously, there's practice problems that help you out, that help you out with these problems. If not, always, come to class and we can, with questions, we can go over some of the problems, okay? Now, let's talk about measurements, okay? Now, the thing about measurements, it represents a number, a value, but with a unit, okay? The unit is important. Now, we do utilize the metric units, but we will be using some of the English units just for practicing how to convert from one over to the other. And so, for example, this comment here, this book weighs 8. It really doesn't give us much information because, what's wrong with this comment? One is at 8 pounds, tons, ounces, etc. So without a unit, it's meaningless. So that's crucial, okay? Now, the other aspect about any measurement is that there is a degree of uncertainty. There is nothing out there that is 100% accurate with respect to this measurement. Because every measurement, there's a degree, always that last digit, where there's a degree of uncertainty, okay? And what we end up doing is to basically guess or give your best guess as to what that last digit is, okay? Now, what governs this guess? Well, that's governed by the accuracy of the tool that you utilize to do a measurement. Now, I understand that if I take two numbers and I multiply them, divide them, and so forth, I can end up on my calculator a number with, 100 digits. And students may be tempted to present those 100 digits as an answer. But I'm here to tell you that will be incorrect, okay? But when it comes to measurements, the thing to remember is this: you cannot be more accurate than the least accurate measurement, okay? And so if I'm measuring the room, and let's say I want to measure the area of this room that I'm in, and in one hand I got a little ruler, on the other hand I got a laser beam. Okay, so I measure the length with the ruler and maybe measure the other distance with the laser beam. Now, obviously, the laser beam is going to give me a lot more digits, a lot more accuracy, right? And now I'm going to take those two numbers and multiply them together. I may be tempted to give the same number of digits that the laser gave me, but that would be incorrect. Why? Because the ruler is the one with the least accurate digits. Therefore, my answer should have no more digits than the least accurate measurement, which in that example would be the ruler. Okay, it's all about the accuracy of your measurement. And as I stated, every measurement has a degree of uncertainty. Some have a degree of uncertainty of plus or minus 1. Some, depending on the instrument you're using, a balance could have plus or minus 0.001. And it all depends on what type of instrument you're using, okay? Now, with respect to units in the metric system, we use units shown up here. CM represents centimeters, MM represents millimeters, M represents meters, KM represents kilometers, okay? And obviously for here, we could be using maybe think something like a ruler to measure these lengths. So I'm going to have another paper here that talks about to break this down, because for some reason, sometimes the metric system kind of throws people for a loop. And what I'm going to do is show you maybe another way to look at it to help you out. Now, the metric system has a lot of advantages and a lot of similarities between length. We're measuring either length, we're measuring the mass, or we're measuring the volume. And the metric system, they're all connected with respect to centi, milli, and kilo. All right, more on that in a bit. So obviously we look at these two rulers and you can see here that the white ruler is not as accurate as the brown one, right? Simply because the number of increments. And so we cannot be more accurate than, say, 1/10 of a place with the white ruler than we can with the brown one. And let's say for, I don't know, for argument's sake, we are measuring, let me make a line here. Maybe we're measuring this distance here. Okay. So you can see using a white ruler that to get a right measurement for that, we're going to have to kind of estimate that last value. We know we're going from 6 to 7 here, right? And we know this is the halfway mark right there. So this is like 6.5, okay? And that line using the right ruler, you know, your guess is good as mine. You can call it 6.3, or maybe you see it as 6.4. All right. It doesn't mean that my number is correct, nor does it mean yours is correct. This is what you observe from your angle, and that's the best number you can give using that ruler. Okay. But notice here that I cannot be more accurate than 1/10 of a place using the white ruler, compared to the brown one, where you can see I got now more increments, so I can see that 6.30. From what I see, 6.30 is what I'm measuring there. And notice that with the brown one, because I have more increments, I can go 2 more decimal places to the 100 place. And so the bottom one is a lot more accurate by the 100 place compared to the top one, the white ruler, which is only accurate to the 10th place, okay? All right, so I know sometimes you're tempted, well, you know, I can guesstimate to the 100 place using a white ruler, but you can't. okay, because you don't have enough increments there. You're estimating at the first decimal place, and that's where you stop it, right there, okay? As far as accuracy, so the top one would be about 6.4, the bottom would be about what, 6.30, all right? Okay. Now, with mass, we use units of milligrams, K also, again, K for kilograms and G for grams. We could also use centigrams for C for centigrams. Now, obviously here we got two means of weighing mass, one on the left, one on the right. The one on the right is a lot more accurate. Okay, this is the type of lab balance that we would use in the actual lab when we were, doing the face-to-face class. And at that one, if you look closely at that picture, I can go to 0.0001 decimal place. Okay, the one on the left, probably maybe 100 place. Not so accurate. Okay. All right. Now mass versus weight. Now here being on Earth, we tend to interchange the two. I'm guilty of it, but technically that's incorrect. Okay, because mass is a measure of all the matter that an entity has, whereas weight is a function of the gravitational force on that chunk of matter, okay? And so weight is really a measure of the force of gravity. So the weight is the mass times the gravity. And that gravity depends on what body of the space you're in. And Earth is an X amount, it's a constant. On the moon, a little bit different. Other planets, it would be a little bit different. So that's why here on Earth, if you weigh 170 pounds, on the moon, you're going to be weighing about 29 pounds. Okay. All right. You haven't done anything to change the mass. You still have the same amount of mass. What is different is your weight. But unfortunately, you're going to see us, especially me, I'm guilty of it, I'm into it, that we interchange the term weight and mass because we're here on Earth. Okay, well, we work out in space will be more correct, if you will. All right, so volume. Volume, some of the units used there are liters, capital L. We can also use kiloliters, or we can use milliliters, okay? Some of the equipment utilized here are shown here. We've got things like beakers and graduated cylinders, syringes. These are all things that can measure volume, different types of pieces of equipment. Now, with respect to units, some of you may be aware of the unit CC. You go to the doctor, you get a shot, or maybe some of you are nurse assistants already and giving shots to patients, and you saying, I gotta give you 10 cc's, okay? Well, 10 cc's represents cubic centimeters, okay? It is a volume measurement, okay? And cubic centimeters, which is centimeter times centimeter times centimeter, the three axes, X, Y, and Z, gives you 1 centimeter times 1 centimeter times 1 centimeter gives you 1 cubic centimeter, which is equivalent to 1 milliliter, okay? 1 milliliter or 1 cc. Those are the units there. Now, sometimes when we have to utilize English units, there's a little tool here to help you out. I always get the pints and the cups all mixed up, but this little picture here kind of helps me out. If you notice, we got the big G here. Let me change the color here so okay? The big G, the letter G. Within the letter G, there are 4 Q's. So what that tells you is that there in 1 gallon is equal to 4 quarts, okay? Now look within the quart, 1 quart, there are 2 P's, which is 2 pints, okay? And within the pints, there are 2 C's. So in 1 pint, okay, there are 2 cups. And so what you have here are three conversion factors, the thing which are nothing more than ratios. So for example, if I take the first one, I can write it with gallons in the numerator and 4 quarts in the denominator. I can write it in that form, or I can invert it. I can say 4 quarts over 1 gallon, okay? 4 quarts over 1 gallon. And I can do the same for 1 quart, 2 pints. So I got a total of 6 different ways to write these conversion factors. Now, which one I utilize depends on the question asked. And keep in mind your general algebra that like units will either, depending on what I'm doing mathematically, they can cancel each other out. For example, if I use the 1 gallon over 4 quarts factor, and I multiply, let's say for argument's sake, by 10 quarts. 10 quarts times this factor. Okay, 10 quarts is like saying 10 over 1, right? Okay. Notice my quarts cancel out, leaving me the units of gallons. And that is what happens when I take the factor 1 gallon over 4 quarts and I multiply it by 10 quarts. That's supposed to be quarts, not G. Okay. And the same token, if I'm multiplying by, say, 10 gallons and I want to get to quarts, I use the second factor where I got 4 quarts over 1 gallon, and notice that my gallons cancel out. It is about units and keeping track of units. We will, with time, eventually set problems up where we got 3 of these conversion factors set up. Now, I know some of you are used to using the ratio system where you got no way to write it, like A over B is equal to C over D. All right. I highly recommend you don't use that here, okay? Unless you're like a 99,000%, 100% sure, because when you start getting into 3 or 4 conversion factors, that can really throw you for a loop. And so what we're gonna advocate is to use these conversion factors, these ratios, and by knowing the units and keeping track of the units, you are able to set these problems up properly, okay? All right, so, and we'll get some examples. So I'll give an extreme example here to show you that if you got conversion factors, you can convert from any unit to any other unit, okay? Now, you will have some problems sometimes where you got to read this diagram, read a volume. And you notice here that you have this is called a graduated cylinder, basically a cylinder that's graduated with units, okay, and numbers. And then ask you, what is the volume that you have here? Now, the thing about this is any type of cylinder that you use to measure, first thing to do is find out where your 0 point is, because that's where your reading is corrected, because we have some equipment where the 0 point is on top and you're reading from top to bottom, or you're reading from bottom to top, okay? But you got to realize where you're at. So make sure you read the right volume. If we look at this graduated cylinder, the 0 part is down here. This is where 0 is. So you're reading from top to bottom to top, okay? And then you notice that a lot of liquids, there are a few exceptions, but a lot of liquids, when they're in the cylinder, they form this curvature. We call that a meniscus. The question is, well, where do I read? Do I read on top of this meniscus or on the bottom? And the answer is this: if you form a meniscus, you extrapolate a line to the bottom of that meniscus, and you read it. You're over here looking at this in that direction. You're reading straight back across to the meniscus, and that's where you take your reading. Notice that you're at 20, so the volume is 20. Actually, the volume is closer to between 20. Here's 21. This is the 21 mark right here. This is like 20 and a half. 8.5 mark right there. And so you're maybe somewhere about 20.6, 20.7. Yeah. maybe 20.6. That's about the best I can, and this would be units of milliliters, okay? If you see 20.7, that's fine. It's reasonable number. I mean, you can get, because that uncertainty is that last number. All right, so meniscus, read the bottom of the curvature for this position. All right, which brings us to the thing about significant digits. Now, here's the takeaway from this whole thing about significant digits. It is not that these values are insignificant. These values do have value. Okay, these numbers have value. When we deal about significant or insignificant digits, we are talking about numbers that will not play a role in determining the number of sig figs, that's shorthand for significant figures, in your answer. Keep it in mind that you cannot be more accurate than the least accurate measurement that you have. And so we need to determine which digits are significant and which are not, because then that tells us how many sig figs we have. And so if I multiply a number with 3 sig figs by another number that has 4 sig figs, my answer should have no more than 3 sig figs, the least accurate digit, okay? All right, so we're going to talk about sig figs and how to determine them. Now, the chapter talks has a set rule for you, and I'm going to go through it, and then I'm going to kind of shorthand it for you. You ask yourself a couple of questions, whether a specific number or zero specifically is 2 questions. If you answer yes to both, then that zero is significant. Because where the confusing part is that zero. Is it significant or insignificant? And that's where it gets confusing. The numbers 1 through 9 always count as significant, so we don't have to worry about those. Okay, so and we're going to have some rules about that. So another example, like we did earlier about a measurement, you can notice that the top one we're accurate at the most by the 10th place. So you can call it maybe 29.2, okay? Whereas the bottom one, you can see it got 29.2, maybe 5. Okay, I can go to the 100th place with the bottom ruler, okay? So the more increments, the higher decimal places I can have. And so the top one has least number of significant digits than the bottom one, okay? Because the bottom one has more accuracy, measurement capability than the top ruler. Okay, so let's talk about determining what are significant figures. So all 9 non-zeros, all numbers 1 through 9 are considered significant, okay? Keeping in mind, we're not talking about value. We're talking about whether it's significant with respect to the final calculations and the accuracy. So in this particular example, 4895.2 contains 5 sig figs, because they're all integers, okay? Which brings us to zeros, okay? So any leading zero, notice these zeros in front of 5454, all they're doing is setting the decimal place, okay? So 0.000, those 4 zeros in the beginning are not considered significant. Does not mean that they don't count. It just means that they're just holding the decimal place. The true value is they're here at the 4th decimal place. And so the numbers 5454 count as significant because 1, they're rule number 1. Okay. So any leading zeros, so that means any numbers less than 1 do not count as being significant. All they're doing is holding decimal places. All right. Now, when you have zeros between integers, they count as being counted as significant. Okay. And so if we look at 3050, the 0 between the 3 and the 5 count, whereas the 0 after the 5 is not surrounded by integers. It's up there all by itself. It's in front of a 5, so it doesn't count. So that number, 3050, has only 3 sig figs. It does not mean that the last 0 does not count as far as value, because I want you to keep in mind, when you look at that digit, you are in the 3000 magnitude, 3000 magnitude of that number. If you were to drop that last 0, guess what? You're at 300. You have changed the magnitude of that value completely, okay? So you don't want to do that. You just know that I'm in the 3000 range, but the last 0 is not significant with respect to sig figs. Okay? If we look at the next number, obviously the first 3 zeros are leading zeros, room number 2, therefore do not count. And the next 2 zeros, the other 2 zeros, are between 2 integers, okay? They're captive, and so they count. So this number, 0.002001, has 4 sig figs. Okay, once I identify that, if I were to do something mathematically between these 2 numbers, specifically, if I were to multiply or divide those 2 numbers, my answer should have no more than 3 sig figs, okay? Because that 3 sig figs is the least accurate number. And whatever I do mathematically, specifically multiply or divide, then my answer can never have more than 3 sig figs. All right, next one. Any trailing zeros after a decimal point and a whole number count. For example, if we look at this as 0.0880, there are 3 sig figs, right? That last 0 is before an integer, in this case 8, and guess what? There is a decimal in that number. So I answered the question. Yes, look at the 0, the last 0. There's an integer in front of it, and there's a decimal point in that number. Therefore, that number 0.0880 has 3 sig figs. Okay, so ask the same question over here. Same 2 questions, or 3050. Ask it for the last 0. We know the 0 between the 2 integers is count. We're asking about the last one right here, the last 0. Well, is there an integer in front of it? Yes. Is there a decimal point anywhere in that number? Answer is no. Therefore, the last 0 doesn't count. Okay. When you answer yes to both those questions for a particular 0, it counts. Take a look at here. Last 2 zeros. Is there an integer in front of those 2 zeros? Yes, there's a 5. Is there a decimal point anywhere in that number? No. Therefore, those 2 zeros are not counted as significant digits. That number only has 3 sig figs. Okay. All right, so if you take that 285, if I take 285 and I put a decimal point followed by the zeros, then those zeros has are count. Therefore, 285.00 has 5 sig figs. Okay. Now, exact numbers. That is any number that is not considered, that is not measured. Okay. Point number 1, I said earlier, any measurement, mass, weight, volume, any type of those measurements they're measurements. And therefore there's the last number, there's some doubt, okay? Some error involved with the last number. But exact numbers, okay, they're exact. So things like 14 people, there's exactly 14 people. It's not 2.6 or 3 or 13, it's exactly 4. A conversion factor, 3 feet per yard. It was exactly 3 feet per yard, as there are exactly 100 pennies per dollar, or 5 pods, or a 12-pack. Okay, those are exact numbers. What that means is this, that these exact numbers would not play a factor in determining how many sig figs your final answer would have. Okay, keep it in mind, that can't be more accurate than the least accurate value that I utilize to do my calculation. Okay, so exact numbers do not count. Things that are not exact, like 7 inches, 200 pounds, 10 ounces, think about it. Those are measurements. Those are measured by some instrumentation. So there's a degree of uncertainty in their measurement, and therefore would be a factor in determining how many sig figs digits your answer would have at the end. Because even though I'm sure, like I said, you can type 2 numbers and you end up with, your calculator gives you a whole slew of numbers. You might think, well, if I give all 7 digits, my number is accurate. Well, that's not correct. You can't think in that means. You have to think in the means of how accurate my tools are that are utilized to do the measurement. Okay. So anything that's measured is not exact. All right, so let's take a look at some digits and determine how many sig figs are in there. All right, so 5.05. Well, if we look at all the integers are counts, so there's at least 2 sig figs in this number. Okay, now the question is at 0. Well, the fact is that they are trapped between 2 integers, automatically they count. If you forget that, then ask the question, is there an integer in front of that 0? Yes, there's a 5. Then the second question, is there a decimal point anywhere in that number? Answer is yes. Yes, yes, the 0 counts. Okay, that's just in case you forgot that any zeros between 2 integers always count. All right, so there are 3 sig figs in that number. 1200, okay? The 1 and 2 obviously count. Okay, what about the zeros? Ask the questions. Is there an integer in front of the zeros? Yes, there's a 2. Is there a decimal point anywhere in that number? Answer is no. Therefore, the zeros are not considered significant digits. Okay, so this number only has 2 significant digits. Okay. This one, 0.02027. Well, you can very quickly break it down. Look at answer the question for the first 2. 1, from the rules, they're leading zeros, so they don't count. Okay, but if you forgot, ask the 2 questions. For these 2 zeros, is there an integer in front of the first 2 zeros? No, there isn't. They don't count. All right. How about the next one? Well, let's look at the next 0 all by itself. Well, the fact that it's in between 2 integers automatically counts, okay? But again, if you forgot, ask the question. Is there an integer in front of this 0 between the 2? Yes, there's a 2. Is there a decimal point? Yes, there is, so that counts. Then finally, the last one, the last 0. Is there an integer in front of it? Yes, there's a 2. Is there a decimal point? Yes. So that means that both zeros count as far as being significant. So this has 4 sig figs. Okay. And then not finally, but this one here, the 4 zeros in front are leading zeros, and therefore there's only 1 number there, the 5. That's only 1 sig fig. Okay. Look at the 50. 50 is 2 digits. The 5 obviously counts as a 0. Ask the question, is there a decimal in front of it? Anywhere in there, the answer is no, even though there is an integer. So there's only 1 sig fig. But the moment you put a decimal point and you add some zeros, they all count. Okay, all the zeros count. There's 4 sig figs in that number. 1, 2, 3.45. All of them are integers. No question about it. They all count. And then finally, the last one, we have 8090. The first zero between the 8 and the 9 obviously count because they're captive zeros. But the last one, even though it's in front of an integer, there's no decimal point in there. So there's only 3. Okay. Okay. So we have to determine how many sig figs that they are, because the next step we're going to break the mathematics into multiplication and division, and then we're going to break it into addition and subtraction. And so when it comes to multiplication and division only, when we are multiplying numbers, like let's say we're multiplying these two numbers and we're going to multiply or we're going to divide, then our answer should have no more than 2 sig figs, okay? If we do the same between these two numbers, multiply or divide between these two numbers, then our answer should have no more than 1 sig fig, okay? Which means that we're going to learn how to round numbers off, round numbers up, or leave the same, okay? All right. Okay, this is a kind of a breakdown, kind of determine whether something's significant or not by asking the question about integer or decimal point within the number. Okay. All right. So before we do any of the mathematics, let's do the rounding. Okay. And the rule's pretty straightforward. Okay. We look at that number that we need to either, we're going to do one or two things. We're going to leave it alone for whatever value it is, or we're going to look at the neighbor, and the neighbor is going to tell us whether that number gets rounded up or stays the same. All right. And so, for example, if you look at that 5.4, like, okay, and for whatever reason, we're gonna need to round it up to round to 5. So we look at the neighbor and we ask the question: is our neighbor less than 5? If the neighbor is less than 5, then that number remains the same. So that 5.4 becomes 5. If the neighbor is greater than 5 or equal to 5, in this case 5.5, then, and we're going to round it off again at the number in front of the decimal point for whatever reason, okay, then we look at the neighbor and determine it's greater than 5, so that 5 becomes 6, okay? Now, the important part about rounding is we only care about the immediate neighbor. We don't care about what is happening down the road, okay? Because I know I've had things where if you take the 5 and you round that up, and that rounds that up, and that rounds that up, no, don't do any of that. Immediate neighbor, that's where it is, okay? And either that number that you're working with, it's either going to stay the same in value or it's going to go up to the next value, okay? Not down. It will stay the same or go up, okay? All right. Now, we're going to be careful not to change the magnitude of your numbers, okay? And so after you do the calculations and you've got everything, look at the numbers you're working with. Look at the magnitude that you're in. You don't want to change the magnitude. For example, look at down here. It says round 5,400 to 1 significant figure. Okay. Well, how do we do that? Well, let's first write that number down. We're given 5400. We need to round it to to 1 significant figure. Okay. Well, we start in the far left of the number and we make note of where that 1 digit, which is the first one. So the 5 is the 1 sig fig position, okay? So now the question is, do we take that 5 and leave it at 5 or bring it up? Well, what do? We look at the neighbor, okay? Using our rule here and determine that is less than 5. So that 5 becomes stays at 5. What happens to the number 4, it gets converted to 0. So this becomes 5,000, okay? Now here's the thing to remember. Any numbers after the decimal point you can drop. It doesn't change the magnitude, okay? If this was, 0.46, whatever, all that could be dropped. It doesn't change the magnitude. Any numbers before the decimal point, like that 4, change to 0. Because if you do not, if you drop the zeros, guess what? You're going to report a 5. Now, what have you done here? Put a dollar sign in front of 5,400. Which is better? You want $5,400 or you want $5? Okay, you're at the 5,400 magnitude. Your answer should, at the 5,000 magnitude, because you're at 5,400. Your answer should remain in the 5,000 magnitude, okay? And that's what this does right here. You're in the 5,000 magnitude, not in the 5 magnitude. So one way to remember is this: any numbers that need to be dropped that are before the decimal point, convert into zeros. Any numbers after the decimal point, you can drop them. It doesn't change the magnitude, okay, of the value of the number you're working with. Okay. Oh, question here. 5,400. Question is, we don't round until we are ready to give the answer. That is correct. We wouldn't want to round before multiply. You are 100% correct. Good point. When you are any mathematics you do, carry out the numbers to wherever they fall, write them out, and then at the end, that is where you start rounding numbers off. Okay, at the end, don't truncate anything until you're done at the end, because that will change your final magnitude. Because the answers, for example, are based on how many sig figs you have at the end. Oh, okay. I just realized this. It is 3:28. Good question. All right, we are done. Let us stop it here. We're about halfway done. We'll knock this out on Tuesday and then jump into chapter 3. So we got chapter 2 and we'll be done in slide 19. We get it, slide 19. Okay. All right. Yeah, let's stop it here. And I think, Josh, you had 5,400. Is that what you were asking? I just saw the note there.
Oh, yeah, yeah. I'm sorry. I don't know how well my mic works, but yeah, I was just saying 5,400 is just 5,400. I mean, that's dollar bills. So
Yeah, exactly. Like I said, your answer should be in the same magnitude. Not dropping the 4 and the 2 zeros, because you end up with 5. Right? You notice back here?
yeah, I mean, I see like it just closes in where it's 5,400 in dollar bills.
Yeah, exactly. What happens sometimes that the students do is they want to round this number off and they report 5. Well, what have you done to the magnitude? You went from a 5,000 range to a 5 range. And so what I say is, well, I'll tell you what, think of that number. You're going to round that 54. Think of that number as, $5,400 versus $5. If your boss said to you, I'm going to round off your paycheck and this is what you're going to get, well, there's a problem with that, right? You want $5,400, or I should say $5,000 versus $5. Notice the change in magnitude. Okay, so whenever you get ready, we'll have some examples we're going to do. the first thing to do is keep track of the magnitude that you're at, okay? And because your answer should remain in the same magnitude. You don't want to lose the magnitude like it's shown here, going from 5,000 to 5. And I just said, throw in a dollar bill in there, and it gives you an idea what I mean by changing the magnitude. Okay?
Yeah, and what's kind of confusing is the way decimals are used in different countries, because sometimes decimals aren't used as well, and there's always commas used, and
Yeah,
that's what makes
exactly.
it kind of confusing sometimes.
I was going to say, because I know in other countries, commas are used instead of decimal places. So if you're used to commas, you got to get used to decimal points here, okay? Because I know if I was in a European country, if I were to write this number as like this, that is to us, that to them, it would mean 5.400, but that's not the case. The commas here are for thousands place. Okay.
I always keep that in mind.
Yeah,
I always ask.
yeah. Commas here for just holding the thousand place. The decimal point is the actual magnitude. Okay, well, I tell you what, guys, let me stop the share. Any other questions? No other questions? Hey, Ruby Rose. We will continue